We know that for getting interference, two conditions must be met. They are: the sources must be coherent, that is, they must maintain a constant or zero phase difference with respect to each other. And second is, the sources must be monochromatic, that is, they have a single wavelength. To produce coherent sources, there are two methods. One is division of wavefront and second is division of amplitude. Light from a monochromatic source is used to illuminate a barrier like small openings or some optical devices like Lloyd's mirror, Fresnel biprism or thin films to produce two coherent sources. The light emerging from these are coherent since a single source produces the original light beam. Based on the method of producing coherent light sources, interference is two types. One is interference by division of wavefront and second is interference by division of amplitude. Interference by division of wavefront is obtained by employing slits, mirrors or biprism or lenses. It requires a point source and a narrow slit source. Interference by division of wavefront can be obtained by the principle of diffraction, example is Young's double slit experiment, by reflection, example Lloyd's mirror, by refraction, example Fresnel's biprism. In Young's double slit experiment, light waves from the single source, when hit two narrow slits S1 and S2, get diffracted, and these diffracted waves superpose and produce bright and dark bands on the screen. And these bright and dark bands are due to interference. And in Lloyd's mirror, light waves from real source and a virtual source S prime, which is due to reflection from the Lloyd's mirror, will superpose and produce bright and dark bands on the screen. In this method, the position of the dark and bright bands are reversed relative to the pattern of two real sources because there is a 180 degrees phase change produced by the reflection at the Lloyd's mirror. Another method is Fresnel's biprism. In Fresnel's biprism, two diverging coherent light beams are created, S and S prime, and these waves superpose and produce interference pattern on the screen. And another method of interference is interference by division of amplitude. Here, the amplitude of the incident beam is divided into two or more parts, either by partial reflection or refraction. Thus, we have coherent beams produced by division of amplitude. These beams travel different paths and are finally brought together to produce interference. The effects resulting from the superposition of two beams are referred to as two-beam interference, and those resulting from superposition of more than two beams are referred to as multiple beam interference. The interference in thin films, Newton's rings and Michelson interferometer are examples of two-beam interference, and Fabry-Perot interferometer is an example of multiple beam interference. And another, the example of thin film interference, division of amplitude is thin film interference. Here, the light wave AB, when it falls on the surface which separates air and some medium which is having higher refractive index, a ray R1 is reflected, which undergoes 180 degrees phase difference because of it is reflected by a denser medium. And another wave R2, after traversing this much path, it will get reflected towards in this path R2. These two waves R1 and R2 are coherent, and this is the path difference. And apart from this path difference, there is 180 degrees phase difference. Therefore, it will produce interference. And T1 and T2 also produce interference because they are also the transmitted waves originated from the same AB. Therefore, here the interference is complementary and reflected and transmitted light, because in the reflected interference, R1 will undergo an extra path difference of 180 degrees. Another example of interference by division of amplitude is Newton's rings. Here a monochromatic source of light S is kept at focus of condensing lens L1. The parallel beam of light emerging from L1 falls on the glass plate G, kept at 45 degrees angle. The glass plate reflects a part of the incident light vertically downwards, normally on thin air film enclosed by the plano-convex lens L and glass plate P. The reflected beam from the air film is viewed with microscope. Alternate bright and dark circular rings with dark spot as center is seen. The amplitude of each incident beam is divided into two parts, one at the top of the air film and another at bottom of the air film.